Hi, I'm Nathaniel Cox, and this is my project on the effect of an extra home game on the home team winning an NBA playoff series. So the setup for this problem is that an NBA playoff series is played in a best-of-7 format, meaning that the first team to win 4 games in the series wins the series. This is set up in a 2-2-1-1-1 format, meaning that the first 2 games are played on the home court of the higher seeded team. Then the next 2 games are played on the home court of the lower seeded team. This happens in every single series. However, they've only played 4 games. Therefore, if one of the teams doesn't sweep the other, more games are needed. In this case, the home field advantage alternates between the home and away team, meaning the 5th game is played at the home of the higher seeded team, the 6th game at the home of the lower seeded team, and the final 7th game, if needed, is played at the home court of the higher seeded team. This means that if a series ends in 5 or 7 games, the higher seeded team gets 1 extra game of home court advantage over the lower seeded team. The main question of our analysis, therefore, is how much does this extra game add to the higher seeded team's win percentage? This is motivated by the fact that the whole reason to get higher seeding is to get these home field advantages in the playoffs. So if it doesn't add too much, then why is it worth it to fight for higher seeding in the first place? All our data comes from basketballreference.com, which NBA data has a goldmine. It has all the NBA data from all the playoff series and regular season games in the history of the NBA. And this data includes all sorts of cool dependent and independent variables for study on any type of project. So the key dependent variable I chose to use is whether or not the higher seeded team won the series. And the key independent variable that we're basing this off of is whether or not the series ended in 5 or 7 games. So some controls that I used to try and control for the fact that usually the higher seeded team is just a better team than the lower seeded team include the following. First, regular season statistic differences between the 2 teams, such as the percentage difference in the regular season win percentage between the higher and lower seeded teams. This gives what percentage more the higher seeded team won in terms of games compared to the lower seeded team. Then I also included the difference in regular season strength of schedule, which I subtracted the higher team's strength of schedule from the lower seeded team's strength of schedule. This controls for the fact that the 2 teams might not have played equally tough opponents during their regular seasons. Finally, I took the difference between the higher seeded team and lower seeded team's offensive and defensive ratings in the regular season, respectively, to try to control for the fact that one of the teams might have been better at offense or defense than the other. I then also took the percentage difference in betting odds for the series between lower and higher seeded teams. The higher this number is, the more the home team is favored over the away team. And then finally, I had dummy variables for the round of the playoffs that the series was played in, with the baseline being a first round playoff series and then including dummies for the conference semifinals, the conference finals, and the finals. So, why am I using a logistic regression here? And what is a logistic regression in the first place? So, a logistic or Logit regression is very much like a multilinear regression, except that our dependent variable has log odds instead of just being in base form. So logistic regression is only used when our dependent variable is Bernoulli, because otherwise it's tough to take log odds. Major assumptions include independence of errors, linearity in the logit for continuous variables, no extreme outliers, and no multicollinearity. My model will not meet all of these assumptions perfectly, but I figured that it's better to have a flawed model than no model at all. While many of these assumptions hold, there are some outliers in the data through very few are extreme, and there's some multicollinearity between some of the variables. Using a logistic regression allows us to have a discrete output. And as we can see, we have multicollinearity plots between all of our variables. And while there usually isn't too much multicollinearity, examples of higher multicollinearity than I am very comfortable with are between regular season win percentage and regular season strength of schedule difference, as well as the odds difference and regular season win percentage. Finally, as well as the difference between the offensive rating and defensive rating. All of these intuitively make sense. Generally, teams that are better at offense struggle on defense. And the reason that this is positive is because the higher a defensive rating is, the worse the defense is. In addition, it makes sense that teams that win more in the regular season are both more favored to win in the playoffs and have played easier teams because it's generally easier to win against easier opponents. So the logistic regression format is usually quite simple. It's just like a simple linear regression, except that instead of our dependent variable being just y, it is the log odds of our dependent variable. In this case, our dependent variable being the probability of the home team winning the series. The only difference that my model has from this baseline simple model is that I have 9 betas with 9 different xi's. So instead of beta 0 plus beta 1 xi, I have beta 0 plus beta 1 x1i plus beta 2 x2i, all the way through beta 9 x9i. So in terms of our prior distributions for our data and that we can use for our JAGS process, because our dependent and main independent variables are both Bernoulli distributed, the beta binomial conjugacy is most suited for the model. A beta distribution will be used for all the controls as well, just to have the conjugacy work well. From there, JAGS will be used to model the regression, first setting up the model and then feeding the data in and the hyperparameter values. We're going to use a 10,000 long chain with a 5,000 burn-in period and a 1,000 adapt period. The chain will also be thinned with a thin value equaling to 20, just to really protect against stickiness. For the model code, I have my y variable being Bernoulli distributed, and then that probability that I'm feeding into the Bernoulli is from my logit that I'm modeling with all my betas and my x variables. And as you can see, all my priors are beta 1, 1 because I know nothing about these priors prior to my data. I want everything to be as weakly informative as possible. So, looking at the output, we have this mean of 0.2, which you're like, wow, that's a big effect, 20%? No, that's not 20%. That's my log odds. And these are really hard to interpret, which means that we're going to have to do some work on this coefficient later. The other thing to take note of are both my relatively large standard deviation as well as the high effective sample size of my data. So what does the output tell us? Again, significance. Because our standard deviation is so high, our result is not significant at the 90% significance level. In addition, because of our high effective sample sizes for all our betas, it suggests little autocorrelation. And that suggestion is verified with our MCMC diagnostic plots for beta 1. As we can see in our autocorrelation plot, we have very, very little autocorrelation. In addition, there's very little stickiness as our chain really explores the space well, and it varies quite a lot between jumps. So no stickiness, no autocorrelation. And because I don't want to include for all 10 of my plots because it would take up too many slides, this is meant to be representative of all my betas because all my betas looked roughly like this. They were all relatively clean. And this is our posterior beta distributions. As shown, as you can see, beta 1 was really not changed from a uniform distribution too much, which means that obviously the data didn't fit the model quite as well as we would have liked. So we ran a posterior predictive check as well, and unfortunately the results are close to 1 and 0 respectively, meaning our model doesn't fit the data too well. The only compromise I made was I checked every 10th draw for drawing from my binomial instead of checking every draw because doing 10,000 draws crashed my computer and therefore I couldn't do it. So in terms of output analysis, the output from this JAGS model doesn't actually give us the size of our effects in terms of the log odds. It only really gives us a direction of the impact of our independent variable. And to account for this, we have to perform marginal analysis. And this involves checking how much the log odds for the home team winning the series change given they play an extra game at home. And luckily, this gives us in terms of probability. So we can actually interpret this quite well. And to do that, we use this formula here. We're basically back solving for probability given our log odds formula from earlier for our regression. And again, this would change from this simple formula to what I'm doing in my model because I have 9 betas. So again, in our exp function, we have to have beta 0 plus beta 1 x1i through plus beta 9 x9i for both top and bottom. For our betas, we're going to have our mean values for our betas from beta 0 through beta 2 through 9, and beta 1 actually, as well as mean values for our x's from x2 through x9s. However, what we are going to do is we're going to plug 0 in once, and then we're going to plug in 1 once for solving for these probabilities. And then we're going to subtract the probability of x1 equaling 1 to x2 from the probability for x1 equaling 0. This x1 equaling 0 subtracted from x1 equaling 1 will give us our size of our effect from adding the extra home game for the higher seeded team. So we do this marginal analysis. There's a lot of betas going on, a lot of x's going on, and we get a effect size of 2%, which isn't very big, especially considering that our effect is not statistically significant. And therefore, our results are that our impact of an extra home game for the higher seeded team on series win probability is roughly 2%. Again, not very big. And given the sacrifices that a team makes to achieve this higher seeding, which is playing harder in the regular season, risking injury to their star players to win more games, this relatively small benefit doesn't really seem worth it. And in terms of some future topics to study, if our analysis could be done with a larger data set, results may be more accurate. And therefore, if we repeat the study in 100 years, assuming the NBA goes on that long, results may be more credible, maybe more significant as well. There are outliers in our data set, with lower seeded teams being favored over higher seeded teams, meaning our odds difference is less than or equal to 1. And this is either due to an injury to the higher seeded team or the lower seeded team not trying as hard as they could have in the regular season to preserve their best players. In addition, there are higher seeded teams that are omega favored over the lower seeded teams. And this could be due to being a super team that is set to win the whole thing, playing against an 8 seed in the first round. And removing these outliers might have made our estimate for beta 1 more representative of the extra home game's actual effect. Thank you for listening to my presentation.